So, thank you for inviting me. Please remain seated. You have no doubt seen this quote before by Carl Sagan, right? Extraordinary claims require extraordinary evidence, many different versions of it. But what does it mean, right? Have you ever stopped to think, what do we mean by extraordinary evidence? Because that's a very subjective thing. So to answer this question, I'm going to call my good friend Rodney. Come on up. Us Canadians have to stick together because, as we've learned recently, never trust Americans. All right, so this is a 60-minute talk that I'm going to try to compress into 30 minutes. So I'm just going to jump right into it. So Rodney, I'm psychic.
All right. What would you like me to do with that information?
I would like you to give me $500,000.
I would prefer not to.
Understandable. But I'm going to prove it to you.
All right.
I had a sense that you might be skeptical. So we're going to design an experiment, okay? What I'm going to do is I'm going to take a coin out of my pocket because I still carry loose change, and I am going to toss that coin 5 times. And I'm going to predict whether it comes up head or tails. And if I can correctly predict those 5 coin tosses, I'm expecting that you're going to give me $500,000.
Well, I think I need more than 5, and I too am an academic, so I could give you $25?
Okay. But why is that not enough? Because if you think about it mathematically, what is the probability that I will get those 5 coin tosses right purely by chance? Well, it's very simple math. It's 1/2 times 1/2 times 1/2. It works out to a probability of 3.1%. And in medicine, as in most fields of science, we use a statistical cutoff of p is less than 0.05. So my question for you, Rodney, why is this not good enough for me, but good enough for a large pharmaceutical company that's trying to get their new drug approved? Why are you a big pharma shill that is moving the goalpost? Right? Because in every other circumstance, you would accept a p-value of less than 0.05. But why are you not willing to accept it here? I ask you.
You got me. It's all been a fraud. I am a shill for the companies. I'm sorry.
But think about it, right? If you think about it, you're like, yeah, why is this different? Because if I had given you a different scenario, if I had said that I was an expert in classical music, and I said, play me 5 songs and I'll tell you whether it's Beethoven or Mozart, would you be willing to accept that I was an expert in classical music?
Not if it's only 2 choices.
Okay.
I would not allow that.
Okay, interesting. He's clearly not playing along with the way this is supposed
yes,
to go.
I would. Yes, I would.
Yeah.
Absolutely.
But, whoops, there you go. Mathematically, it's the same thing. All right, so yeah, fine, okay, 2 choices. But think about it. Why are you more willing to accept, I presume you are more willing to accept the possibility that I am an expert in, back, there we go. Why are you more willing to accept the possibility that I'm an expert in classical music and not willing to accept that I'm a psychic? Because mathematically, those are the same thing. So there's an online poll feature which sometimes doesn't work if we're not on the McGill University campus. So let's take a second. If you guys can get up and vote, do it. If it doesn't work, we're not going to spend more than 5 seconds on it. This is a remarkably buggy program that McGill makes me use. But I want you to vote. Am I a psychic? Am I an expert in classical music? Or am I not getting to the point of what's supposed to be a statistical talk? So you can actually sit down, sorry.
All right.
Yeah, okay. It works in class. It doesn't work when I leave McGill University. I don't know why. Anyways. The point is, mathematically, these are the same thing. So why are we more willing to accept one versus the other? Because by pure math, they're the same. So why? Okay. The issue is the difference between frequentist and Bayesian statistics. And you may not have heard of these terms before, but it's important to understand them. So if you don't know how frequentist statistics was started, it's a fascinating story. I'm going to recommend this series of books to you because we don't have a lot of time to get through these issues. But The Lady Tasting Tea, and that refers to the story that Ronald Fisher, who was a great big name in the field of statistics and also a firm denier that cigarettes cause lung cancer, because no one's perfect, but he developed the p-value to evaluate whether this woman that he knew could actually taste whether the tea was added to milk or milk was added to tea. That is why the p-value exists, to answer this very specific and very, very obscure question. And he developed something called the null hypothesis, which most people learn in their statistics class, which is funny because I don't know why they still teach the null hypothesis in class anymore. I read a study that disproved it years ago. But if you don't understand why that's funny, ask your neighbor. So he developed the null hypothesis, and what he said was, the null hypothesis is never proved or established, but it is possibly disproved in the course of experimentation. And so if you don't have a methods background, you have to understand what we're doing with the vast majority of statistical techniques. We're not actually trying to prove our hypothesis true, which is kind of bonkers when you say it out loud. But what we're trying to do is we are defining with the p-value the probability of observing results as or more extreme than the experiment if the null hypothesis is true. But we don't actually know if the null hypothesis is true. We can never actually establish it. So this is a trivia question when you have students like define a p-value, and it's very hard to do because it is such a counterintuitive definition. And so frequentist statistics have a fundamental weakness because they are non-intuitive. And the way we explain them to people is actually wrong. And the way we think about p-values is actually wrong, but we all do it. A much better way to understand statistics is Bayesian statistics. So Reverend Bayes was a minister. My apologies for the skeptics and atheists in the audience. He was actually defining a mathematical model. And again, this is a very weird story. His idea was, I'm going to turn my back on a billiards ball table and throw billiard balls onto the table. And my assistant is going to tell me if it goes to the right or to the left. And based on those answers, I'm going to narrow down where I think the center ball is located. It's this very, very weird theoretical example that he was working out. But his idea was that I'm going to refine my theory with each subsequent piece of data that I get. So Bayes developed this theory. He then died, never published it. It was actually published by his friend. And a lot of the mathematical model was developed by Pierre-Simon Laplace later. And so there's been the perpetual tension between the English and the French about who actually should have the claim to this theory. And if you want to learn more about the history of Bayes' theory, I'm going to recommend this other book to you, The Theory That Would Not Die. And it goes through the history of how Bayes' theory was invented, forgotten, and then rediscovered. But the basic idea is that you start with a hypothesis, and then you accumulate data until you are satisfied that you have either proven or disproven it. Now, if you think about it, this makes a lot more sense. This is how we tend to think, and this is how most of the lay public thinks science actually works. So there's this great tension between frequentist and Bayesian statistics. And the reason why we use frequentist statistics is, unfortunately, that the math to do Bayesian statistics and the computers to do Bayesian statistics simply did not exist until relatively recently. But I'll talk about that a little bit later. But to show you what the problem is, and to put this into a concrete example, because I realize this is a bit obscure for people, we're going to use an example from the Thinking Fast and Slow book. So some of you may have read the book, you may know this example, so don't scream out the answer if you know it. But this is the story. You get this description of Steve. Steve is a very shy and withdrawn person, invariably helpful, but with very little interest in people or in the world of reality. I like him already. A meek and tidy soul, he has a need for order and structure and a passion for detail. So the question is Steve more likely to be a librarian or a farmer? So the online voting system is not going to work. Just raise your hands. Who thinks Steve is going to be a librarian based on this description? A lot of you have read the book. Who thinks Steve is going to be a farmer? Yeah. So why? Because this description more closely matches the description of a librarian. But that presumes that it's equally likely that somebody's going to be a librarian or a farmer. But you have to go into it realizing that farmers are going to be, there are more farmers than there are librarians in the world. Now that may change over the next 50 to 100 years, but the point is, where's my clicker? The point is, these numbers are arbitrary. But if you assume that there's 20 times more farmers than librarians, And if you want a video on this, I recommend this one from the channel 3 Blue 1 Brown. They go through it in a much more interesting graphical interface. If you assume that there's 20 times more farmers than librarians, then we can do some very, very quick math. Let's assume that the description that we have applies to librarians 5 times more often than it applies to farmers. Well, we can do some very quick math. If you had 2,000 farmers, let's say 10% of them are going to be shy. Okay, so you're going to get 200 shy farmers. If it's 5 times more applicable to librarians, you're going to have 50% of the 100 librarians are going to be shy. So if we looked purely at the shy people that we have out there, because this is a description of a shy person, about 80% of them are going to be farmers. This type of 2x2 table is frequently used in medicine, and it's the difference between sensitivity and specificity and the alternative statistics of positive and negative predictive value. So I'm not going to bore you with this because the actual numbers don't matter. But the point is, did you go into this example thinking that farmers and librarians are equally likely employment opportunities for most individuals in the US? Or did you make some sort of calculation that they are not the same? Did you account for some of your prior pre-existing data on this subject? So let me give you a more concrete example that I deal with on a daily basis. Let's say you are referred a 20-year-old woman for a stress test. I'm a cardiologist by training. That's what I do as my day job. I can tell you that the sensitivity and specificity for a stress test is 70 and 80%, okay? You do a stress test. You want to find out if this woman has heart disease. Let's say the stress test comes back positive, okay? A frequentist is going to say, I'm going to assume that this patient does not have heart disease and see if I can disprove it. Okay, so I assume my patient does not have heart disease. I do the stress test, which is positive. I ask myself, how likely is it that she would have a positive stress test if she doesn't have heart disease? And I know that the answer is 20% because that's 1 minus the specificity. Okay, analogous to the p-value in research. So I cannot reject the null hypothesis. I'm left with this very sort of equivocal result. If I was a Bayesian, though, and I was looking at the same data, I would say to myself, okay, before I do anything, how likely is it that a 20-year-old woman is going to have heart disease? I know that that's going to be pretty low based on everything that I know about heart disease. I arbitrarily say there's a 0.1% chance that she has heart disease. So I know that the sensitivity is 70%. So of those 10 patients with heart disease, 7 will have a positive stress test. 80% of the patients without heart disease will have a negative stress test. I do some numbers. I find out that 7 out of 205 of the patients with a positive stress test are going to have a heart disease. That's a prediction value of about 3.5%. So a frequentist says, I can't disprove the idea that she does not have heart disease. A Bayesian says, I do the stress test, which is positive. I update my pretest probability. I calculate my new probability. And then I write a passive-aggressive consult note back to the referring physician about why you shouldn't do stress tests in young women, because their pretest probability is so low. Clinically in medicine, this is what we do all the time. We start with data, we get more data, and we keep updating our diagnoses. Our diagnoses change. And yet that's not how we do it in most medical, and in fact, most scientific research, okay? The problem with frequentist and Bayesian statistics is that frequentist statistics are a guarantee on process, not on results. A frequentist statistic says if I do the same study in the same way multiple times, I will get the confidence intervals will contain the true answer 95% of the time. It's like when you do a political poll, the results are accurate 19 times out of 20. But you don't know if your poll is the correct one or not, right? The interpretation of frequentist statistics is very non-intuitive and doesn't help us answer the actual question we have if our study is right, if our patient is sick. And so Bayesian statistics are a very different thing, which are a guarantee on results. The way we actually do it, pre-computers, we used to use something called the Sagan normogram, where we would calculate the pretest probability, then take out a ruler and draw a line and get the post-test probability. Now it's all computerized. But basically, what you're doing is you're taking the post-test, you're taking the pretest odds. Do I have a pointer? You're taking the, no, I'll do this one thing. You're taking the pre-test odds, multiplying it by the likelihood ratio to get a post-test odds, and if you work out the math, it still comes out to 3.4%. Same answer as before. Formally, you will see Bayesian statistics usually listed as something like this, okay? The likelihood of the data times the prior distribution divided by a normalizing constant, or more accurately, there we go, probability of the hypothesis times the probability of the evidence given the hypothesis divided by the probability of the evidence. Written out usually as a way like this, the dash means given. So the probability of B given A is equal to the probability of B times the probability of A given B, blah, 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 blah. Let me give you a practical example. Let's go back to my claim of being a psychic. We need to define where all these terms are. So what we want to know is the probability that I am a psychic given that I can predict 5 coin tosses. What we need to know is the probability of me being a psychic. So what is my pretest probability, right? How likely do you think it is that I am a psychic given that what you know about me? Susan's giving me a thumbs down, which is very hurtful. And then you need to know what is the probability of me getting 5 coin tosses right if I am a psychic. What's the probability of me getting 5 coin tosses right if I'm not a psychic? And what is the probability of me not being a psychic? So you realize a lot of these are complementary things. Okay, so the probability of B given A is what we need to know. What is the probability of being a psychic? So you shouldn't say 0, right? I get that, but you should never say 0 because that's actually not scientific, right? You're saying that something is impossible, and nothing is impossible, right? Nothing is technically impossible. It might be very, very low. But if you think something is truly 0, then you shouldn't do the experiment. Right? That's medical ethics, scientific ethics. Don't do a study if you already know what the result is going to be, especially when you're talking about experimenting on people, okay? So, yes, very, very low. We're going to arbitrarily make up a number. We're going to say 0.001. You can put whatever you want, right? The point is going to stay the same. What is the probability of predicting 5 coin tosses if I'm a psychic?
0.3% or 3.1%?
No, what's the probability of me getting 5 coin tosses correct if I'm a psychic? 100%.
Oh, I'm sorry.
One,
Sorry.
yeah.
If you're a psychic, sorry.
What's the probability of me predicting 5 coin tosses if I'm not a psychic? Yeah, that's the binomial theorem, 0.03125, right, 1/2 to the power of 5. And what's the probability of me not being a psychic? 0.99. Okay? So you plug all this in. And this seems like complex math, but it's really not because it's basically, if you look at it objectively, okay, so what's the probability of me being right, of me being a psychic? Well, 0.01 times 100, because I did get the 5 coin tosses correct, right? This is what you're doing if I get the 5 coin tosses correct. So it's the probability of me being right times the probability of me being a psychic, and then you're basically just doing a weighted average of the 2 probabilities, that I would be right if I was a psychic and that I would be right if I wasn't a psychic, okay? And the numbers work out to 0.0311. So what you're actually saying here is a much more intuitive thing. Based on what I saw, the 5 coin tosses being correct, there is a 3% chance that I'm being a psychic. So even though the p-value is low, even though I did something incredible by getting those 5, even though I did something statistically unlikely by getting those 5 coin tosses correct, it's still not enough to convince you that I am a psychic, because your pretest probability was so low. But there is conceivably a threshold where you would be convinced that I was a psychic. Otherwise, Rodney would be out of a job and evaluating. So where can we set the threshold? Well, what if I got 20 coin tosses in a row? Would that be good enough to convince you that I was a psychic? And people are like, well, maybe, I don't know, maybe. What's extraordinary mean? Maybe it's good enough. That's the thing. We don't have to be subjective about these things. We can actually evaluate it because the math is exactly the same. Okay? Oh, yeah, sorry, this is just for the music. So what if we do the 20? Well, here all we're doing is we're substituting out 0.5 to the power of 20. You plug the same numbers into the formula because the pretest probability has not changed. It turns out that now your post-test probability becomes 99.9%. The power of Bayesian statistics is that you can take the same scenario and set different evidence thresholds to prove whether something is true or not. Now, there's a fun little math twist to this. Is getting 20 coin tosses in a row good enough for Rodney when he has to hand out $500,000 to a psychic or somebody with ESP? What's the math problem here? This is a very mathy thing, so I apologize. What's the twist here?
Expected value.
Sorry?
Expected value.
Sort of. It's more fundamental than that. If I put out a call for a $1 million prize or a $500,000 prize that it is now, a lot of people are going to show up. So it's not the probability of one person getting 20 in the row. It's the question of how likely is it that if 1 million people show up, one of them will get 20 in a row. And again, the math is a little bit more complicated. How does this number change if there's 1 million psychics? Well, it's a little bit more complicated, but not substantially so. You just have to put in a number of 0.61 because it's the probability of 1 million people getting it wrong, and then 1 minus that to figure out what's the probability that at least one of them will get it right purely by chance. You plug it in, and you still get a very low number. But the point here is not to sort of convince you that math is great, because it is. I think that goes without saying. But we tend to be very subjective in our argumentation that, oh, this is not good enough, right? The data is not good enough, the data is not strong enough. We don't have to be subjective about it. And I think that's the point I wanted to sort of make here. I am a little bit short on, oh, you've got to stop talking now. So there's a lot more to this talk. I'll show you very briefly another video if you want to learn about Markov chains, and we'll keep it on time. The point is, I'll recommend this video from Veritasium if you want to learn more about Bayesian statistics and how it applies to the real world. But this is the point I want you guys to learn about. Learn about Bayesian statistics. I think it is going to be the future of statistics, and I think it's going to be a more useful way to approach pseudoscience, because we do get a lot of bad studies where they say, oh, the p-value is less than 0.05, good enough. No, it's not. Extraordinary claims require extraordinary evidence, but that relies on us to realize that there's more than a binary outcome to medical research. So, thank you very much.
Can we do questions?
Yeah, I'll do question.
Okay, questions.
Choosing the prior still feels a little subjective to me.
Yes, it does. And so great. It gives me an opportunity to do that. It is subjective, but everything in science is subjective to some degree. Every decision you make when you're analyzing data is a subjective decision, right? And the power of Bayesian statistics is that you can have multiple priors. You can have a skeptical prior, you can have an enthusiastic prior, you can have a non-informative prior. So you can ask yourself, is my data good enough to convince a person who believes in this product, a person who's neutral, or a person who's a skeptic? And so you might have enough data to convince somebody who's enthusiastic, but not enough to convince somebody who's a skeptic. And so the subjectivity of Bayesian analysis is its fundamental strength. You can have a much more complex analytical framework that also incorporates prior data. The problem with a lot of studies, and I'll give you a very quick example in cardiology about chelation therapy, where somebody published a study called the TACT trial, which claimed that chelation therapy was good for heart disease because you're removing heavy metals. Complete garbage. Later disproved 10 years later. But he was like, look, I did the study, the p-value is 0.05. And I was like, but we know chelation therapy is garbage. You should have had a different prior probability because your claim was so extraordinary. But the frequentist framework is not set up for that. And so a philosophical rethink in how we design our trials under a Bayesian framework would address that particular problem.
I agree.
Anyone? Yeah.
Thank you for your presentation. The way we teach statistics, or the way I learned statistics was more a decision tree. I will have to compare two medias, use the test. I have to compare three medias, use ANOVA.
Yeah.
How do you see it's going to be possible to change this kind of teaching between the frequentist one to the Bayesian one?
Yeah.
Because the professors just know the frequentist one.
Yeah.
And it's a huge problem because I don't see in the near future this change for at least in Brazil.
Yeah.
I don't see this shifting between the frequentist teaching and the Bayesian teaching. And I would like to hear what you think about it.
Well, as Max Planck said, science advances one funeral at a time. But here's the problem. Bayesian statistics was mathematically impossible for any type of complex model until computers came around, right? Until the 1980s, and frankly the 1990s to be practical, you couldn't do Bayesian statistics beyond very, very simple examples with pen and paper. So there is a whole generation of people that never learned Bayesian statistics. And so until there's a sea change, it's never going to happen. But we do get into this problem of you go, in this store, the hot dogs are always fresh because everybody eats there, and everybody eats there because the hot dogs are always fresh. People learn Bayesian statistics, so they end up teaching Bayesian. They learn frequentist statistics, so they end up teaching frequentist statistics. So it's going to require a new generation of students to get faculty appointments and start teaching and start conducting their trials in a Bayesian way. And it is being done, but it is going to take like a generation to change.
This is great. I use the false positive example in my
Yeah.
book to
Yeah.
really emphasize why replication is needed.
Yeah.
Right, in science. And you're exactly right that we too often take a single study, reach the p-value
Yeah.
that we needed, and so the study must be true, right? My comment is about your coin toss
Yeah.
example, and I'm not sure how this works into Bayesianism or not. The problem is I wouldn't be convinced by 20 coin tosses, because I would be too suspicious that you're a magician and you're not telling me, right? And even if I looked at the coin to see if it was weighted, and I looked for a trick or whatever, and I couldn't figure it out, right? I would still think that you were pulling one over on me, right?
Yeah.
Once a show on Penn and Teller's Fool Us, they get fooled.
Yeah.
They can't find the trick, and yet they never conclude that the person actually has magic powers.
Yeah.
So in the same way, even if you did 20 in a row and I couldn't figure out what the trick was, I still think, yeah, but there's a trick. I'm just not smart enough to figure it out.
Well, here's the problem. Bayesian statistics doesn't solve every problem in science. It doesn't solve fraud. Like if somebody wants to make up their data, we have surprisingly no ways to stop them, right? Which is shocking. If people actually knew that, they would get like really, really upset. There is really no way to stop somebody from just making stuff up. So it doesn't solve every problem. It doesn't solve fraud. It doesn't solve, data. But it is better.
Sure.
It is incrementally and philosophically better because the numbers mean what we think they mean. Because most people think a small p-value means this is unlikely. That's not what a p-value means. And our statistical framework is flawed. And now that the computers have gotten so powerful, hail Microsoft, we can actually do Bayesian statistics in a way we couldn't do it before. And the programs, which used to be extremely obtuse and hard to use, I don't know if anybody ever had to use WinBugs, which was a terrible program. It's now easier. So we can do it, but it's going to take that generational shift.
Yeah, nice.
Okay, I'll take two more and then we'll break for coffee.
Yeah.
Thank you. Thank you for your talk. This made me really happy because I took a philosophy of medicine class a year ago, and something that I really struggled with was Bayesian statistics.
Yeah.
And I feel like you answered one of the questions I had, but then it brings about another question.
Yeah.
In that philosophy of medicine class, one of the things we were addressing is like, okay, so how are we defining disease?
Yeah.
And then how does that affect so if it's a subjective test, depending on how you're defining the disease, like it's gonna really affect your results.
Yeah, but that's okay. You can have different thresholds for diagnosis, right? If you have a test result where it's like, okay, well, our threshold is 10 versus our threshold is 20, our threshold is 30, you're going to get different results. But that's okay, because it means that we can actually have the argument about where our testing threshold should be in an objective fashion, rather than relying on what we often do, which is resorting to eminence-based medicine. Well, I think this. Why? Because. That's not good enough for me. Like, no, but quantify it. That's the power of Bayesian statistics. It allows us to quantify the subjective and to have multiple different outcomes. It's good enough in this scenario, not good enough in this scenario. And now we know. And it also liberates you from the dichotomy of a p-value less than 0.05%. If I told you that this cancer drug was better than another cancer drug 86% of the time, would you take it if you had cancer?
How much is it gonna hurt me?
Let's say they're exactly the same. Would you take it? I would. It's 86% better. But that would not meet the threshold in a classical frequentist model where we require a 95% threshold for everything. So not everything needs to be 95%. Sometimes it needs to be higher if you're trying to claim that you're a psychic, but sometimes it can be lower. If you have cancer, wouldn't you take an 80% shot? I would. We don't have to be so rigidly defined by the p-value of less than 0.05%, which Ronald Fisher himself acknowledged was a completely arbitrary number. He picked it out of a hat. So we can evolve because now the computers are allowing us to be a little bit more subtle in our statistical methodology.
Okay, last one.
Has one. Start twice.
You can flip a coin.
So this campaign to switch to Bayesian, which I think does have a lot of benefit. I think they're from the Netherlands, and they have offered a free stats program that does both.
Yeah.
And do you remember the name of it? I can't remember.
Are you referring to Windbugs with David Spiegelhalter?
I don't know.
Yeah.
It doesn't sound familiar, but it could be. But you know, you could put in your stuff, and it would come up with the usual SPSS frequentist. But then, like, there's another tab, and you can see the same results. And I think their hope is that we're giving this away for free. People will, get more comfortable with it.
It used to be harder because you needed a specific program. And now, all of the major programs, whether it's SPSS or SAS or R or Stata, they all have built-in subroutines. So we've gotten to the point where now the barriers to use are no longer there. It's just the willingness. And just to throw one thing at you, the issue is that if you put a non-informative prior, let's say you have no prior research on a subject, you get the same numbers with the frequentist and the Bayesian results. A lot of people are like, well, what's the point? And the idea is the interpretation is different and the philosophy is better. So we just have to sort of condition people to that and realize it's a little bit extra work, but not that much. There you go.
Okay, thanks, Chris. This was amazing.